Assalamualaikum warahmatullahi wabarakatuh. We continue our part B for the chapter 1. So we look at example 1.4. So a rod of diameter 20 mm and length of 150 mm move at a speed of 25 meter per second in a 50 mm diameter cylinder filled with oil. Okay, if a 12 Newton of force is required to maintain the speed of the rod, calculate the dynamic viscosity of the oil and kinematic viscosity of the oil if relative density of the oil is 0.92. Okay, this is the rod with diameter 20 mm and the length of the rod 150 mm. Okay, and the cylinder here. Okay, a cylinder filled with oil. Okay, this is the rod. Move at a speed of 25 in a 50 mm diameter cylinder. So this is the cylinder with oil fill. Okay, so calculate the dynamic viscosity of the oil and the kinematic viscosity of the oil if the relative density of oil is 0.92. Okay, so given the value here is F is force 12 Newton, diameter rod 20 mm, length of rod 150 mm, and the velocity here 20 meter per second, and the diameter cylinder is 50 mm. Okay, so we look at the shear force of A here. So using area impacted by the shear force area is pi times by d times by length. So we get this value. So look at the shear stress here. Using this equation, shear stress is equal to force divided by area. So we get this value here. Okay. So also shear stress using these equations also. So we can use the shear stress using this equation. Force divided by area, or use this viscosity, dynamic viscosity du over dy here. So we get the value using this is 25 and the dy is 0.015. Okay, you can look at the previous slides, the value there. So we get the dynamic viscosity here. So we get this symbol of dynamic viscosity of 0.7639 meter second per meter squared. And we get the kinematic viscosity using this equation. Kinematic viscosity is equal to dynamic viscosity divided by the density here. So we get the value of 8.30 times by 10 power of -4 meter squared per second here. So this is kinematic viscosity. So we look at the other example 1.6. So a thin plate located 0.1 mm away from a rigid boundary requires 1.2 Newton per meter squared force to move at a speed of 2.5 meter per second. So we have the plate here and the rigid boundary here. Okay, so the u is the velocity of 2.5, the move of speed 2.5. So this is the velocity. And this is the plate located away from the rigid boundary. Okay, the distance. Okay, so the distance between the plate and the rigid boundary. So given distance between plate and rigid boundary dy is 0.1 mm. So we get convert to meter. So we get 0.1 times by 10 power of negative 3 meter. So the plate velocity is 2.5 meter per second. So change in plate velocity is du. So du is u minus y0. Okay, because this is the rigid boundary here. So this is velocity. So you when the du over u minus by 0, because this is the rigid boundary between the plate and the rigid boundary. So you will get the 2.5 meter per second. So force on the plate F is 1.2. Okay, the force they give you in 1.2 Newton per meter squared force. So we have to find the shear stress here using these equations. So just put all the value you get from here. 1.2 here for the force. Okay, so you get the force, also the shear stress here. So we get the value of dynamic viscosity is 4.8 times by 10 power of negative 5 Newton second per Newton. So we get the value of dynamic viscosity of the fluid. Okay, that contained between the plate and the rigid boundary. So we get this equation. We get this value from this equation, from the shear stress equations. Okay, look at example 1.7. We have the velocity distribution for a flow over a plate is given as this one, Ku. This is the velocity distributions, where u is the velocity in meter per second, in unit of meter per second, at a distance y measured above the plate. Okay, if the dynamic viscosity is 0.85 Newton second per meter squared, calculate the velocity and shear stress on the boundary and at 2.25 meter from the boundary. Okay, find u and shear stress at y is equal to 0 and y is equal at 2.25. Okay. So they calculate the velocity and shear stress on the boundary. Okay, boundary is 0. Okay, at the y distance is 0 and at 2.5 meter from the boundary. Okay, so find this value. So given, okay, viscosity here is 0.85 Newton second per meter squared. And this is the velocity distribution. So we get the distribution, velocity distribution, and using the du over dy. Okay, from these equations, you must use using the du over dy. So we get this equation and use the shear stress equation and put this equation to this equation here. So we get the shear stress, okay, at y is 0, du over dy is use equations. So we get the 5 second at y is 0. Okay, so the shear stress here, so we get 4.25. So at y is 0.25 meter, so we get the du over dy. So we get this, okay, 1 second. So we get the shear stress is 0.85 here. Okay. So if you don't understand what this one, so we can discuss in Google Classroom or in our Telegram group. Okay. So I have just explain about this example. So if you don't understand, so you can ask me later. Okay, so 1.2 properties of fluid for the thermodynamic properties. So it's important when temperature affect fluid properties. Okay, ideal gas law. So the thermodynamic properties, we use the ideal gas law. Okay, P times by V is equal to N times by R times by R. So where P is absolute pressure in kilopascal, V is equal to volume of gas in liter. T is absolute temperature in Kelvin. Okay, M is moles of gas. R is gas of constant. Okay, sorry, M in N is, okay, M is, this is N, okay. Just correct these symbols. This is N, okay. N is moles of gas. Okay, since is the periodic table of elements, this is on chemo that you have learned in the previous on diploma or in your STP. So you have this table in elements. Okay, so look at example 1.8. So what pressure will be exerted by 20.16 gram hydrogen? Okay, this is hydrogen gas in a 7.5 liter cylinder at 20 degrees of Celsius. Okay, so the given V volume is 7.5 liter. T, the temperature is 20 degrees per Celsius. Okay, to find from Celsius to Kelvin, so you must plus the 273.15. So we get the 293.15 Kelvin, okay, for the temperature. So the mass 20.116 gram. Atomic weight H2 for the H2. Okay. So 2 times by 1.008 is equal to 2.1016 gram per molecule. Okay, so gram for molecules. So you can look at books at the reference book that I've give you the link to access. Okay, the books reference that HF frame white. Okay, so you can look at the material. You can download from the material that I've upload in Author and also the Google Classroom. So you can look at the reference books. Okay, this is the exactly right or wrong about the value for this. Okay, this one. Okay, so number of moles is, okay, we get the 20.16, okay, times by this atomic weight H2. So we get to 10 mole, 10 molecules. Okay, ideal gas law PV is equal to nRT. Okay, so we just use this equation and put all the value that you get from here. So we get the pressure, absolute pressure is, okay, 3249.67 kilopascal. Okay, so look at example 1.9. Okay, so it's also same as the previous slide. Okay, so just use this equation to find the density, specific weight and specific volume for the gas. So we get the density, and after we get the density of F of the gas, so we find the specific weight. So use this equation. So we get the specific weight of the gas and specific volume. Just put all the value that you get from the density, from the specific weight, and we get the specific volume here. Okay, that's all for the properties thermodynamic gas. So now we look at the surface tension. Okay, surface tension. The symbol of the surface tension is theta S here. So surface tension is a drop of blood forms a hump on a horizontal glass. A drop of mercury forms a near perfect sphere and can be rolled like just a steel ball over a smooth surface. So water droplets from rain or dew hang from branches or leaves of trees. So this is the how surface tension is applied. Okay, this is applied on a drop of blood forms a hump on a horizontal glass. Okay, a drop of mercury and a water droplets. So Surface tension is a property of the surface of fluid that allows it to resist external forces. So due to cohesive forces between molecules, unit of surface tension is force per unit length or energy per unit area. So use in unit Newton per meter. Newton per meter. Okay, example of surface tension values are water and air. At 20 degrees of Celsius, we get 0.073. When water and air at 100 degrees of Celsius, we get the surface tension 0.058 Newton meter. And the mercury and air is equal to 0.1 Newton meter per length. Okay, so this is the application of surface tension. This is part of the first. I have explained the previous slide. So this is okay, the second, and this is the third. For the how it apply in surface tension in fluid mechanics here. Okay, so look at this. Okay, the cohesive forces between molecules below the surface are shared with all neighboring atoms. Those on the surface have no neighboring atoms above and exhibit stronger. So this is free surface here on this is air and this is on liquid. Okay, they have A, B, C, D is the molecule. Okay, the molecule of the liquid. Okay, the molecule in the liquid. So A, B, C, D. Okay, this enhance of the intermolecular attractive force at the surface is called surface tension. Okay, from the molecules in liquid here, okay, they transfer from the depth of the liquid to the surface. So this surface is called the surface tension. Okay, between the air and between the liquid. So this is called the surface tension. Okay, water droplet. Okay, water droplet, the force here and surface tension here. So the force between the water droplet, okay, and between the water and the air. So they have the forces here and we get the surface tension. Okay, this is a force acting on the droplet. Okay, atmospheric pressure here. So we get that this is diameter. So we get this is between the surface tension and the force here. So we get the pressure force. Okay, this is called the pressure force, total of tension force or pressure force. Okay, this in equilibrium of the other fluids. We get this is surface tensions for the other fluid, the different fluid here. When water in 0 degrees of Celsius, we get a 0.076 until the water is 300 degrees Celsius, we get the surface tension of this one. So the other liquids is the difference. Okay, so the surface tension also difference. Okay, we use in equilibrium of pressure force equal to surface tension. We use this equation. Pressure for P is the pressure is equal to 4 times by surface tension. This is 4 times by surface tension divided by D. D is diameter. Okay, look at example 1.10. A water tank is filled with air through a pipe to produce bubbles. Compute air pressure required by the pipe to form bubbles with diameter 10 mm at temperature of 30 degrees of Celsius. Assume atmospheric pressure is 0. So the atmospheric pressure is 0. So given D is 10 meter, diameter of 10 mm is equal to 0.01 meter. So surface tension of water is 0.0712. So you can look at this value from the previous slide that show you that the tables between the different fluid and the surface tension. Okay, so we get the surface tension of the water at 30 degrees of Celsius. We get this one. Okay, therefore the pressure required P using this pressure and surface tension equation. So we just put all the value here. P is equal to 4 times by 0.0712 divided by 0.01. So we get the pressure is 28.48 Newton per meter second. Okay, we get this value. Okay, so the other properties of fluid is capillary action. So capillary action is occurs when one end of capillary tube is immersed in a liquid. All forces holding a liquid together are called cohesive forces. So the forces of attraction between a liquid and another surface are adhesive forces. So this is the capillary effects. They have the water here, H2O, and the rod here. So when the liquid is using the water, so the water rise up to the tube here. So we call this as the capillary. Okay, so the water rise up in the rod here. But when you use the Hg is mercury, so the capillary effects on mercury is not raised up to the rod here. They just raise up here, but it is still immersed in the fluid here. So the forces are attractive between a liquid and another surface are adhesive forces. Water rises in capillary tube because the adhesive force between the water and glass are quite strong, sufficiently strong to draw the liquid up against the force of gravity. Okay, so this up here. Okay, when the four liquid in mercury, the cohesive force are greater than the adhesive forces. Okay, so the cohesive forces are greater than the adhesive forces, so that the level of the liquid inside the tube is actually depressed. Okay, this is not increased there, it just depressed, but this one is increased. The capillary inside the H2O is increased here. Okay, so contributes to ability of plants' roots to take up of water and dissolve nutrients from the soil and transmit them up the stems, and ability of paper and clothes towels to absorb water. Okay, look at the example here of the between this is the road using the capillary effects for the H2O, but this one is capillary effects for the mercury. Okay, this first road is water and the second road is mercury here. So they have the meniscus here. Okay, but this is like this one. Okay, so H2O. Okay, so their look of the rise of the water here like this one. But for the mercury, they have meniscus here. Okay. The meniscus on the liquid surface is a concave U shape. Okay, this is U shape for the rod with water, because the forces between the water and the glass are stronger than between water molecules. Okay, but the meniscus on the surface of the mercury is convex dome shape, is like the dome shape here, because the attractive forces between mercury atoms are stronger than the attraction between mercury and the glass. Okay, so this is also the concept of the capillary tube. Okay, so the adhesive more than cohesive, so they have the concave meniscus like this one. Okay, U shape here. Okay, using the water here. Okay, but the adhesive adhesion less than cohesion. So this get the convex meniscus here. Okay, dome shape here. So the dome shape is the glass between the mercury, but the U shape here, the glass between the water and the glass. Okay, so surface tension force using this equation, surface tensions pi times by d times by surface tension cos theta. Okay, weight of water column and tube is pi over 4 times by d squared over times by h times by specific weight. So just remember this is surface tension force and this. So that is in equilibrium. So we get these equations until we get the height of the capillary rise here. H is the capillary rise between the water to this U shape, and the H capillary depression of the mercury from the dome shape here to the capillary H here. So we use this equation H is equal to 4 times by surface tension times by cos theta divided by specific weight times by diameter. Okay, cos theta is this the angle from the rod to the U shape here for the water here, and also the glass rod with the mercury, so they have the angle here. So this we use the cos theta here. Okay, for water and glasses, okay, the theta is not same as a zero. They have a value, okay, not a zero. Okay, so for mercury and glasses, theta is between 130 degrees to 150 degrees of angle. Okay, degrees. Okay, so the angle of the mercury and glass for water and glass is same as the zero here. Okay, we look at example 1.11. Compute the minimum diameter of glass tube if the capillary rise in the tube does not exceed 0.25 mm. Assume the surface tension of the water is 0.075 Newton per meter. Okay, given H is 0.25 mm, surface tension is 0.075 Newton per meter. So we use this equation here. H is equal to 4 times surface tension times by cos theta divided by specific weight times by D here. Okay, because the minimum diameter of glass tube if the capillary rise in the tube does not exceed 2.25, assume the surface tension of water. Okay, so the surface tension of water, so we use the fluid of water, so they have no angles here. They have the angle here cos theta is 0. When the cos theta is 0, we find the value of 1. Okay, that's why we get the H is equal to 4 times by surface tension times by 1 divided by specific weight times by diameter. So we get this. Okay, and we get the D is 0.1223 meter for the diameter of the glass tube. Okay, so look at the example 1.12. Compute the rise of water when a glass tube of diameter 1.2 mm is placed inside a water tank. Okay, surface tension. Okay, we get the surface tension at this temperature from the table from the previous slide. So we get the surface tension here 0.0728 and capillary rise H, because this is water. Okay, we use the water, so that's why angle is 0. Angle is 0, so cos theta cos 0 is equal to 1. So we just only use this equation. So we get the H 0.0247 meter. So, and compressibility and bulk modulus. The last part of the fluid properties, we get the bulk modulus E defined as the ratio of the change in pressure to the rate of volume. Okay, so this is just using the equations. So where dP is the change in the pressure causing a change in volume dV when the original volume was V. The unit is the same as the pressure Newton per meter squared. So the negative sign indicates reduction in volume due to increasing pressure at normal pressure, and pressure in water is this one. In air is this is bulk modulus. Okay. So compressibility is a measure of the relative volume change of fluid as a response to external pressure. Okay, 1 over E compressibility. Okay, so this is the problem. Okay, try do this problem as your tutorial. So until next week, we can discuss about this problem. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. That's all until we stop to chapter 1. Okay, next week we can discuss about this chapter 1. on Tuesday. Okay, thank you.